So now that we have learned a little bit about parametric curves, we are going to generalize a lot of the ideas from calculus to them. So for example, we're going to learn how to find derivatives of parametrized equations, which will let us find tangent lines, and if we can find second derivatives, intervals of concavity. We're also going to learn how to find areas and arc length and surface area as well. So the first question is, how do you find the equation of the tangent line to the curve defined by x equals f of t and y equals g of t? And so this comes from the chain rule, and this is not always the way the chain rule is explained, but one way to explain it is to say that dy dt is going to equal dy over dx times dx over dt. And you can see how those x's sort of cancel-ish. And I say ish because it's not exactly how it works, but it's good enough for now. And what we want to find is we want to find this dy dx. And so dy dx will be dy dt divided by dx dt. And what you can think of to remember this is that those dt's kind of cancel, which gives you back this. So to find the slope of the tangent line at any xy point, you differentiate the y-coordinate, this g of t function, divided by the derivative of this x function, the f of t part that gives you the x-coordinate. So this is the parametric form of the derivative. If you have a smooth curve, what that means is that there are no corners, given by the equations x equals f of t and y equals g of t. Then the slope of the tangent line is given by the derivative of y over the derivative of x. Pretty simple. And you have to also assume that dx dt is not zero. If that's the case, you're going to have an undefined slope or a vertical tangent line. Okay, so let's find an equation of the tangent line to the curve x equals t cosine t, y equals t sine t, at the point where t is equal to pi. So dy over dx, the slope of the tangent line will be dy dt over dx dt. And just backtrack for a second. To find an equation of a tangent line, we need the slope, and we also need the point that we go through. So let's just find the slope first. So now don't forget about your calculus 1. You've got to remember that there's this thing called the product rule. The derivative of t sine t will be 1 sine t plus t cosine t. The derivative of t cosine t will be 1 cosine t minus t sine t. The slope we will find by inputting pi. So m is sine pi plus pi cosine pi over cosine of pi minus pi sine pi. Okay, so sine of pi is 0, cosine of pi is -1, minus pi times 0. So it looks like my slope is pi. Now the other question is, how do you find your point? You need the x and y coordinates. Well, you use the fact that t is pi and you use your original equations. The x coordinate is given by t cosine t. So the x coordinate is pi cosine of pi, which is -pi. And the y coordinate is pi sine of pi, which is 0. And then to get the equation, we use the point slope form of the equation of a line. Y minus y1 equals m times x minus x1. So y minus 0 equals pi times x plus pi, or y equals pi x plus pi squared. So there is the equation of the tangent line. We can also find all the points on the curve where the tangent is horizontal or vertical using the derivative. So for this, let's note that, so first dy dx is equal to dy dt over dx dt. So dy dt is 2t, and dx dt is 3t squared minus 3. So the tangent will be horizontal if the numerator is 0 and the denominator is not, so we'll just have to double check that the denominator is not. That implies that t is 0, and when we input 0, the denominator is not 0, so we're all good. Now, t equals 0 is not actually the point on the curve where the tangent is horizontal. That tells you what to plug in to get that point. So if t equals 0, then the x is 0 cubed minus 3 times 0, which is 0. And the y-coordinate is 0 squared minus 3, or negative 3. So at the point 0, negative 3 is where that tangent is horizontal. And it's vertical if you have an undefined slope, and that will occur when 3t squared minus 3 equals 0. Which means 3 times the quantity t squared minus 1 is 0, or 3 times t plus 1, t minus 1 is 0. So it looks like at t equals positive negative 1, there are two places where we have a vertical tangent. So at t equals positive 1, the x is 1 minus 3, or negative 2. And the y is 1 minus 3, or negative 2. So we have a vertical tangent at the point negative 2, 2. And also at t equals negative 1. In that case, the x will be negative 1 plus 3, or 2. And the y will be 1 minus 3, which is negative 2. So we have another vertical tangent at the point 2, negative 2. Finding the second derivative is a little bit more tricky. It's not as easy as the first derivative. So we need to find the derivative of the first derivative. That also can be expressed as d squared y over dx squared. And so how you figure this out is you note that the first derivative, d over dx of y, is d over dt of y over d over dt of x. It's just that we wrote that as dy over dx equals dy over dt over dx over dt. That's the same thing. So the difference with the second derivative is instead of differentiating y, so that y is this y, you input dy dx for the y. So input dy over dx into that equation. And that's going to give you d over dt of dy dx over dx dt. So the thing to note that it's not d squared y dt over d squared x dt. So that's a really common mistake. Don't say that it's that. So what this formula is saying is differentiate the first derivative and divide by dx dt again. So let's actually apply this to a particular example. So given x equals t ln t and y equals t plus ln t, find dy dx, and so the first derivative and second derivative. So dy dx, that's dy dt, over the derivative of x with respect to t. So that will be 1 plus 1 over t over 1 minus 1 over t. And let's simplify that by multiplying the numerator and denominator both by t. So that simplifies to t plus 1 over t minus 1. Doing this will make taking the second derivative a lot easier. So here is your first derivative. Now remember that you find the second derivative by replacing the y in the first derivative's equation by dy dt, or dy dx, excuse me, sorry, I said the wrong thing. So this is the derivative of dy over dx, which we just found, divided by dx dt. So the first thing we have to do is differentiate the derivative that we just found. So for that you should use the quotient rule. So the derivative of upper function, which is 1, minus upper function, derivative of lower function, which is 1, over lower function squared. So there is the numerator, over. Now here is a place where students often make mistakes. They want to say that this, right down there in the denominator, they want to say, oh, t minus 1, same as that denominator. Except for this denominator, because we simplified, is not actually the derivative of x. So go back to your equation for x, and what is the derivative of that? It is 1 minus 1 over t. So not t minus 1. So if you simplified it all, you can't just say that that denominator is dx dt anymore. Dx dt was 1 minus 1 over t, which is not the same thing as t minus 1. Okay, now we have to simplify this, which will be a little bit gross, but you can handle it. The numerator is negative 2. The denominator is t minus 1 squared. And in my denominator, I will have t minus 1 over t. Okay, so to deal with this, I can reciprocate the denominator and multiply, which gives me the second derivative is negative 2t over t minus 1 cubed. Okay, now we're also asked to find the t values for which our curve is concave up. So we make a sign chart to determine when the second derivative is positive. So you got the sine of d squared y over dx squared. So this second derivative will be either 0 or undefined at 0. Second derivative is 0 there. Undefined at 1. And then we just pick various test numbers to determine the sign of the second derivative on these subintervals. So, for example, a good test number to the left of 0 could be negative 1. When you input negative 1, the numerator is positive, the denominator is negative, so overall your second derivative is negative on that interval from t being negative infinity to 0. Between 0 and 1, a reasonable test number could be, say, a half. Your numerator is negative. Your denominator, well, negative 1/2 minus 1 is also negative. Cubed is negative. So there your second derivative is positive. And past one, say test 2, numerator negative, denominator positive, overall you're negative. So you have that the curve is concave up on the interval from 0 to 1 because that is where the second derivative is positive. And this specifically, be careful, this is actually t values. Those aren't x values. So it's when you plug those t's in, the range of points that come out are going to produce a curve that is concave up. Now the next question, the next thing we'll do is finding areas under curves. So how do you find an area under a curve that's traced by a parametric equation? So first let's assume we have a curve y equals f of x between some a and some b. We want to find the area if we have something parametric. So how we found this with calculus 1 was to do the integral from a to b of f of x dx, or written a slightly different way, that's the integral from a to b of y dx. And if we have the parameterization, say x equals f of t, y equals g of t, and we have the curve is traced from some alpha to some beta, this could be written as the integral from alpha to beta. Well, y will be g of t, and dx, well, dx dt is the same thing as f prime of t, so therefore dx is equal to f prime of t dt. So times f prime of t dt. Now, one thing that can be a bit tricky with this is that you have to make sure that alpha equals f of a and beta equals f of b. So it could be the case that in your first integral the lower bound is less than the upper bound, but in your second integral they switch. So that ordering can be a bit tricky, and we'll talk about it in a few examples. Now that would be if you had a curve that was sort of y as a function of x. How would it change if x was a function of y? So if you had instead x equals f of y, and you had some sideways curve, okay, and we'll call that a and we'll call that b now. Well, then the area was the integral from your a to your b, and it was f of y dy, or that just changes to x dy. So it's just the opposite of what you've got there. So, and in that case, this formula would become alpha to beta with some fussing to make sure that they're in the right order. F of t times g prime of t dt. So same idea. Personally, I think it's easiest to think about them in this form and in that form. Okay, so here is that just restated. And now let's use this to find the area under an ellipse. So x equals a cosine theta, y equals b sine theta between 0 and 2 pi. So you can convince yourselves that when you graph this, so plugging in some numbers, you have an ellipse where you extend from a to negative a in the x direction, b to negative b in the vertical direction, the y direction, and you go in this order. This first point corresponds to theta equals 0. This point over here corresponds to theta equals pi. So the first thing that I observed is that the area of this ellipse is twice the integral from negative a to a of y dx, whatever that equation might be. So I'm saying, okay, well, if I take 2 times that area, we're good. You could have actually even said that it's the same thing as 4 times the area from 0 to a of y dx. That's also totally fine. All right, let's just use the second one because usually having 0 is helpful. All right, now plugging in y and dx is not so hard. We'll leave the bounds off for now. So y is b sine of theta dx, so the derivative of x will be a sine, well, negative a sine theta d theta. So let's just factor out that negative for ab integral sine squared theta. Now the question is what to do about those bounds. Now, here's the thing you have to notice is that that value of a, that's achieved when theta is equal to 0. So this upper bound actually becomes the 0. And this value here, the value of, say, x being 0, that's achieved when theta is pi halves. That lower bound is pi halves. And because it really bothers me when the lower bound is bigger than the upper bound, I'm going to swap them and negate the integral. So I have 4ab times the integral from 0 to pi halves sine squared theta d theta. Okay, now to integrate sine squared theta, you have to use your half angle identities. So we have 4ab times the integral from 0 to pi halves 1/2 1 minus cosine of 2 theta d theta. So that's the same thing as 2ab times theta minus 1/2 sine of 2 theta evaluated from 0 to pi halves. Okay, so that's 2ab times pi halves minus, it's going to be sine of pi, which is 0. And then inputting 0, we're going to get a big fat 0 minus 0. So it looks like the area of an ellipse is just pi AB. And here is at least one reason, additional reason, because this is what we just did, is totally a reason as well, to believe that this is true. A circle with radius r, its area is pi r squared. And the circle is the case when A is equal to B and they're both equal to R. And notice that when you plug R into that formula, you end up with pi times R or pi r squared like you're supposed to. All right, now let's do another one. Let's find the area enclosed by these curves and the y-axis. Now it's best here, you need to actually graph these curves to figure out what's going on. So let's plot some points. So T, X, Y. So if T is 0, the X is 0, and the Y is 0. If T is 1, the X is 1 minus 2 negative 1, and the Y is 1. And my inclination is to plug in T equals 4, and the X is 2, and the Y is 16 minus 8, or negative 8. So here's what's happened. I left a space there on purpose. So your curve started at 0, 0, went back to negative 1, 1, and then all of a sudden it's at 4, 8. So way the heck over there. So point is the curve crossed the y-axis at some number in between, and we just need to figure out what that number is. So hopefully it's something nice, but what you're looking for actually is where is this thing equal to 0. So x will equal 0 if t times t minus 2 is 0. So it turns out that when you input 2, the x is 0 and the y is root 2. So that's the point. Y equals root 2. So and the other tricky thing about this question is that you have an upper curve and a lower curve. It's just the upper curve happens to be the y-axis, or the line x equals 0. So the area here would equal the integral from y equals 0 to y equals root 2. And I'm going to say xr minus xl, where xr is the curve on the right and xl is the curve on the left. But in this case, that xr curve is 0, and we have xl is just some curve we don't happen to know the equation of. So 0 minus xl dy. Okay, so now let's use the parameterization instead. So it turns out that the point y equals 0 corresponds to a t value of 0. And y equals root 2 corresponds to a t value of 2. And we'll have negative, so that's x dy. So x is t squared minus 2t. And then dy will be the derivative of y, which is 1/2 t to the negative 1/2 dt. And it gets a little bit ugly, so let's simplify it. So integral from 0 to 2. So we have negative t squared plus 2t times 1 over 2 root t dt. Let's distribute that 1 over 2 root t, and that will give us the integral from 0 to 2, negative 1/2 t to the 3/2 plus t to the 1/2. And the exponents are a little bit disgusting, but from here you should be able to get the integral. So the antiderivative is negative 1/2 t to the 5/2 times 2/5 plus t to the 3/2 times 2/3, evaluated from 0 to 2. So you have negative 1/5 times t to the negative 1/5 times 2 to the 5/2 plus 2/3 times 2 to the 3/2 minus 0. And so simplifying that slightly, so 2 to the 5/2 is the same thing as 2 to the 1/2 and 2 to the 4/2. So it looks like 4 root 2. So minus 4 root 2 over 5. And similarly, 2 to the 3/2, that's going to be 2 to the 1/2 times 2 to the 2 over 2. So 2 plus 4 root 2 over 3. And then just get a common denominator. Multiply the first one by 3, negative 12 root 2 over 15. Second one by 5, 20 root 2 over 15, which gives us 8 root 2 over 15. Now these questions are finding the area, and they mean it when they say area. They don't mean signed area. They mean that area should be a positive value. So if you get a negative value, you possibly got your bounds mixed up and put in the wrong order. Now we can also generalize the arc length formula, and this could be pretty useful because maybe your parameterized equation represents a road and you want to be able to figure out how long that road is. So the basic arc length formula, way back when, is the integral from a to b square root 1 plus f prime of x squared dx. And that could be written as 1 plus dy over dx squared dx. And well, let's replace dy over dx by our derivative for the parameterization. So we're just going to assume we've got some alpha to some beta. once again, be a little bit fussy about the order. We'll have 1 plus, well, dy over dx is dy over dt over dx over dt, that whole thing squared. And because I need t's, I'm going to change this dx into dx dt times dt, and you can think about, okay, those dt's kind of cancel, so it's like, okay, and it's the same thing as before. And I'm going to take this dx dt, I'm going to put it into the square root. And when I put it into the square root, it gets squared, and it cancels with this dx dt that's in that denominator and multiplies by that 1, giving us the equation integral alpha to beta root dx dt squared plus dy dt squared dt. And so another way to think about that is that's the same thing as taking the parametrized equation for your x. So that's your, was f of t, f prime of t is squared, you add on g prime of t, and you square it, dt. And that's the equation for arc length if you have a parametrized curve. So here is arc length in parametrized form. So these really should say alphas and betas, so alpha, beta. All right, let's use that to prove that the circumference of a circle of radius r is 2 pi r. So we know that x equals r cosine theta, y equals r sine theta for theta from 0 to 2 pi. That is a parameterization of a circle. So s equals integral alpha to beta. This would be dx dt squared plus dy dt squared dt. Okay, so we have 0 to 2 pi. Okay, dx dt is negative r sine theta, that quantity squared, plus dy dt, which is r cosine theta, quantity squared, dt. Simplify that slightly. Inside the radical, we have r squared sine squared theta plus r squared cosine squared theta, which is say d theta, not dt. And factor out the r squared. We have r squared times sine squared theta plus cosine squared theta. There's your favorite trigonometric identity. Sine squared plus cosine squared theta equals 1. So it turns out all we have here is the integral from 0 to 2 pi of r d theta. That's it. And the antiderivative of r d theta will just be r theta, evaluated from 0 to 2 pi, which when you input 2 pi gives you 2 pi r. So you just used that arc length formula to prove that the arc length, or the length to go all the way around a circle of radius r, is 2 pi r. So let's do this one more time. What is the length of the curve traversed by x equals sine 2t, y equals cosine 2t from 0 to 2 pi? So remember here, this was a circle with r equal to 1 traced twice. We did this in an earlier lesson. So let's see what happens when we try to find the arc length using these equations. So 0 to 2 pi. Dx dt squared plus dy dt squared dt. So 0 to 2 pi. Okay, so don't forget your chain rule. Dx dt is going to be 2 cosine of 2t, that quantity squared, and dy dt will be negative 2 sine of 2t, the quantity squared. So notice how we're going to have a greatest common factor of 4 times the quantity cosine squared 2t plus sine squared 2t dt. And cosine squared 2t plus sine squared of 2t is also 1 because both the sine and cosine have 2t in them. So we have the integral from 0 to 2 pi of 2 dt, or 2t evaluated from 0 to 2 pi, which is 4 pi. And now here is the slight problem. It just depends on what the question is asking. If the question is asking how far has the particle traveled, then 4 pi is totally fine, but the actual length of the curve is really 2 pi because it was a circle with radius 1. So you have to be a little bit careful that you answer the question you're asked. So if you're asked just what is the length of the curve, remember that curve is just the set of points, not how it's traced, versus parametric curve, how these points are traced. So if your question was how long is this curve, well then you would actually have had to integrate from 0 to pi, because that's how long it took to traverse the curve once. So just be aware of the fact that these parametric equations could occasionally double back on themselves, and you should be aware that that might be going on. Okay, and the last application to calculus we're going to discuss is the area of a surface of revolution. So once again, from long ago. So we found that when you rotate around the x-axis, so the easiest way I have to think about this is to think about a picture. You have something being spun around the x-axis. You have to have some way to account for how far away you are, or the radius, and some way to account for the length of that little chunk. And so the surface area in this case is the integral of 2 pi y, this distance is y, ds. And ds is that expression we had for the arc length, which in the case of parameterizations was dx dt squared plus dy dt squared, that quantity rooted. And so you think, okay, well, the circumference is 2 pi r, and my r is varying because it's not constant, so this is given by y. And ds, the length of the curve, is that little arc length thing. That's how this relates to arc length. So that's for the x-axis. If we're talking about the y-axis, well, then the only thing that changes is that instead of your radius being a y, now it's an x. So it's 2 pi x ds. And the ds expression is the same for either of those. And so the only difference here with parametric equations is you're going to have x equals some f of t, y equals some g of t. And so in the case of the x-axis, you use g of t for the y, and you use f of t for the x in the case of the y-axis. That's what these equations say. I think it's easier to remember them as 2 pi y ds and 2 pi x ds, and then just think, okay, well, my y is equal to g of t, therefore that's what I plug in. My x is equal to f of t, and that's what you plug in. And then ds is just the expression from arc length. So it's all about circles today. Well, and spheres. So three-dimensional circle. Prove that the surface area of a sphere with radius r is 4 pi r squared. So the way that you can obtain a sphere's surface area is by taking a semicircle of radius r and spinning it about the x-axis. So, and you could do about the y-axis too, but let's just stick to the x-axis. So the surface area will be integral 2 pi y ds. The parameterization of a circle that we usually use is x equals r cosine theta, y equals r sine theta. So let's plug that in. So 2 pi y is r sine theta. And ds will be the square root of dx d theta squared, so negative r sine theta squared plus r cosine theta squared d theta. And the angles range from 0 to pi as we traverse that circle. So we have 2 pi r integral 0 to pi sine theta. Inside this root we have r squared times sine squared theta plus cosine squared theta. And so taking out that r squared, so an extra r there, we have 2 pi r squared times the integral from 0 to pi of sine of theta. Now the antiderivative of sine of theta is negative cosine theta. So that's 2 pi r squared times negative 1 minus input 0, negative 1. Looks like 2 pi r squared times 2, or 4 pi r squared. That's a lot to process in one lesson because we did a whole bunch of calculus ideas with these equations, so we'll spend the next lesson just doing a few more examples of each of them.